Hey, it's Dr. J. I'm back today with a few loose ends from 6.4. I just looking over the video, I realized after I'd run out of time that I didn't get a chance to talk about the natural log graph. And the common log graph. I spent so much time on the base 2 and the base 3 and other bases like that, but I didn't get around to doing these. They're important, especially in the future sections, 6.5, 6.6, when we start doing the properties, and the most important thing is the applications. So let's go ahead and do these two today, and then tomorrow we'll continue with the properties of logarithms. Just a couple examples. So graph f of x is ln of x plus 5. So that would be the natural log, ln, logarithmos naturalis, ln. Now we need a mother table, right? You can't just, I mean, you could, if you're, I shouldn't say you can't, you certainly can do whatever you want. You can plug in whatever numbers you want and such, but I like to find a mother table that we've used before, and so that would be the ln, y equals the ln of x, which is the same thing as x is e to the y power. Yeah, remember the log form and the exponential form are just reversing the roles. I like to call this heads, and this is like tails. They're two sides of the same coin. So remember, when we make these tables, you're going to have a lot of decimals. Your y values are -2, -1, 0, 1, and 2. Remember, your y values are the same as the x values from your exponential graph. Now you're going to have to use a calculator for these. We were able to get away without using a calculator when we were using like base 2 and base 3 and base 4 and things like that, but you're going to need a calculator for these. So you're going to do e to the y, yeah? Or you could do the ln of x, but I don't know what x is yet. Right? We're trying to figure out what x is, so I'm going to use e to the y, and that's going to tell me what x is. So it's kind of like x is acting like in the previous chapters or previous sections what used to be y is now x. You probably remember a lot of these, at least you might be familiar with some of them. I'm only going to do 2 decimals, so 0.14, 0.37. This one you could do by your head. Yeah, anything to the 0 power is just 1. E to the 1 power, that's 2.71. Or technically it's 2.72 if you round it, but I always memorize it as 2.71, so let's just leave it that way. And then e squared, 7.39. All right. If the homework asks you for more than 2 decimal places, it's probably not a graphing question. It would be a question where it's just abstractly asking you what the value is. But if it's a graphing question, you can do 2 decimal places. Once I start using my board here, my graphing board, I'm only going to do 1 decimal place. Okay. We should also figure out the vertical asymptote. We definitely did this one in the last lecture. The vertical asymptote, you set the argument equal to 0. Remember, for the domain, I'll just do a quick refresher. For the domain, it's greater than 0. It's good to know both of these. It tells you where to put your graph. Your graph is going to be way over here at -5. x is greater than negative 5. Oh, we haven't done our transformations yet. So we're going to add negative 5 to all of our x's. You're wondering what that blank stare was. I was looking at my table going, wait a minute, we haven't done our transformation. This is the mother table. Yeah, this is mom, M-O-M. You have to transform the mother. We're not graphing ln x, we're graphing ln x plus 5. Remember, plus 5 actually means minus 5. You're shifting everything to the left. That's pretty easy to see, I hope. Now look at the domain and the asymptote. Clearly everything is going to the left 5 units. So I'm going to need a new table here. Let's see if I can squeeze it in right here. There is no vertical shift, so the y values are going to stay the same. Let's just go ahead and put the y values in now. Negative 2, negative 1, 0, 1, and 2. And the new x values are going to be, I don't need a calculator for that, negative 4.86, negative 4.63, negative 4. Notice all of these numbers are greater than negative 5. Let's see, negative 2.29 and positive 2.39. So that everybody could see clearly, I'm going to try to count. My scale is 1, 2, 3. So I'm expanding my grid a little bit so it's easier to see. Negative 1, negative 2, negative 3, negative 4, negative 5. On your homework, the first thing you want to do is plot the asymptote first. And then pick 2 of these points from your transform table. Don't use the mother table. The mother table's gone. I want the transform table. The middle row is always going to be a nice point, and then you're just going to have to get lucky and pick one of these other ones. You don't really have to get lucky. Just pick one that looks reasonable, and you can do that. So negative 4 and 0 is right here. I'm going to plot them all. Let's see, negative 4.86 and negative 2. So really close to the asymptote. Negative 4.63 and negative 1. Still pretty close to the asymptote. I put it closer to negative 4.5. Negative 2.29 and 1. So let's see, negative 2.29. So right about here. Now there's negative 2, there's negative 3. So right about here. It doesn't have to be perfect. All right. So not quite to negative 2.5. And then this one's way over here at positive 2.39 and 2. So right about there. And there you go. So this is the graph. F of x equals ln x plus 5. The domain, negative 5 to infinity. The range, free answer, negative infinity to infinity. And the VA, the vertical asymptote, is right here at negative 5. Okay, so that's your natural log graph. If you do this in the homework and it doesn't mark it right because your decimals are off a little bit, you can send me an email and I'll grade it by hand. I'll just take one look at it, and if it looks good, I'll mark it right. Right. If it's upside down or backwards or something, you're going to have to do it again. But I mean, as long as the graph looks like the right graph, I don't want you spending 2 hours trying to get these decimals to match. The tolerance is about 0.5. So as long as you're about a half a unit, less than half a unit away from the actual number, it should mark it right. Okay. Should mark it right. All right. So that's the natural log graph. I got one more example, and I'll get this up there quickly. We do have another lecture coming on the properties of these logarithms, in particular the natural log and the common log, so it's important that we got this done today. Example 2. Let's graph y equals 8 minus log x. Not log x minus 8, but 8 minus log x. Couple things I want to mention before I get into it. If you don't see a base, this is the common log. Base 10. All right. Some people like to put a little 10 right there. Occasionally I'll do it. Maybe at the beginning of the section you might see that. So we're going to use a common log base table, which is much nicer because it's powers of 10, which come out very, very nice. Okay. Another thing I like to do is rewrite it like this. This negative is actually an invisible -1, and the 8 is actually a +8, not a -8. Sometimes when your brain sees a number followed by a negative sign, it's just human nature to immediately think that that number's negative, but it's not. That negative is actually a multiplier, a reflector, -1, and the 8 is actually a vertical shift of +8. So we're going to use the common log table. Remember, the y's are always -2, -1, 0, 1, and 2. The x's are powers of 10. Let's start at the bottom. They're really easy. What's 10 squared? I can hear you through the internet. 100, right? Probably won't fit on my graph paper, but I can still put it down on my chart. What's 10 to the first? 10. What's 10 to the 0? 1. Yeah. These are all powers of 10. Okay. These are powers of 10. The x's are powers of 10. Yeah. X is 10 to the y power. What's 10 to the -1 power? 1/10, or 0.1. And 10 to the -2 is 1/100th. You probably won't graph the biggest and the smallest. They just won't fit, especially on this board that I have. I would need a really big board. I don't even think my board back in the classroom, remember that board we had off to the side? I don't think it's big enough. All right, now we got our transformations. So we're going to multiply all the y's by -1. We're going to add 8 to all the y's. And we're going to do nothing to the x's. So there is no horizontal shift. Nothing is happening to the x, see? X is just x, so x is just x. Just leave it alone. X stays x. Now we go through our transformation. And we're going to get our new y's. Oh, look how nice those come out. That should happen. If you start with a nice mother table, you transform it, you end up with a nice offspring table is what we call it. For practical purposes, I will not graph the 100 and I will not graph the 100th. I'm just going to graph these ones here. Okay. I mean, if you want, you got a big piece of graph paper, or you just want to stretch out your paper a little bit and mark that as 100, you certainly can. Actually, it would be way over here sideways, because X is 100 here. Before I draw the graph, I just want to pause and have you look at this for a second. Think about what's missing that we had on all the other graphs. The VA is missing, yeah? The VA, you're going to set the argument equal to 0. Oh, look! You don't have to do anything. The argument is just X. You set it equal to 0. You're done. That's it. That's your VA. Yeah? It's also your domain. Set X greater than 0. Yeah, you're done. There's nothing to do. Whenever there's no horizontal shift, your vertical asymptote and your domain are always going to be 0. Yeah? Greater than 0 for the domain and equal to 0 for the asymptote. So on my graphing board, this time I'm going to count by ones because I've got to go all the way to 10. I don't think I could do if I do 1, 2, 3, 4, 5, 7, 8. Yeah, I can't get there. So we're going to count by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 and 7. Oh, shoot. I should have planned that out a little better. Let's put my x-axis down here. Nice thing about using whiteboard. Hopefully you're using pencil at home so that you can erase if you need to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 10 and 7 right there. Oh, I forgot to put my asymptote. I was talking about it a minute ago, but I didn't draw it. It's right on top of the axis. X equals 0. That's your VA. That's your vertical asymptote. And I'll erase it here. It's kind of getting in the way of my other points. You know, on your homework, you could just plot these two, 10, 7 and 1, 8. And you're done. Oh, I missed the point there. It's very, very flat. And then when it gets close to the x-axis, it turns. And these decimal points here that you can't see, they are so close to the x-axis. So this point here at 9 is so close to the x-axis you can barely distinguish it. It's just barely touching the x-axis. And now you see why I'm not plotting the point at 106, because I'd have to go way over here to 100 off the chart, and then it would be, the y value would be 6 if I was way over there. So there you go. That's your graph. It kind of looks like a straight line. I mean, it's so straight, but it's slightly bending down, curving down towards negative infinity, and then it's sharply, abruptly taking a turn vertically and going straight up to infinity. All right, you probably know what I'm going to ask last. What's the domain and the range? So the domain, 0 to infinity. The range, negative infinity to infinity. All right, and your asymptote you already have is x equals 0. Okay, so those are your loose ends for the graphing. The next lecture coming soon will be the properties of logarithms, followed by some applications that we'll get to soon. Okay, Dr. Jordan signing out. Bye.